Okay, folks, so I want to look at some terminology here. This is the idea of linear operators, or sometimes called linear transformations, and superposition. So the fundamental idea that we want to introduce is that of a linear transformation. One of the things that's going to be difficult about this new idea of a linear transformation is that we've really been looking at linear transformations through our entire math career. We just haven't used this particular vocabulary word. Okay. So I just want to warn you, at this point we haven't yet defined vector spaces, so really this definition isn't going to make sense from a mathematical foundation standpoint, but we can go ahead and start talking about these linear transformations, and then once we get to defining vector spaces, we can start looking at this definition more precisely. So what you should focus on is, don't worry about this notion of vector space yet, but focus on the notion of linearity. Okay. So let's let V and W be two vector spaces. Again, we're not quite sure of that expression yet. Think of it as one place where some objects exist and a second place where some objects exist. And L is going to be a mapping. L is going to be a mapping from V to W. Going forward, to shortcut me having to write that, I'll just say L is going to be a mapping from space V to space W. Okay. Then L is said to be a linear transformation if for two objects in the first set and for a real number, or sometimes a complex number, if we have L of V1 plus V2 is equal to L of V1 plus L of V2. Similarly, if L of that abstract constant, in this case alpha, V1 can be written as alpha times the linear transformation of V1. This is saying that linear transformations distribute over sums. Of what? Well, these are called vectors. You can just think of them as objects for right now. So linear transformations are the transformation that distributes over the sums of two vectors, and we can say that the constants factor out. Okay. Again, I highlighted this already, but I just want to say it one more time. One of the things that's going to be a little bit confusing about this notion of linear transformations is that you've been encountering them throughout your entire math career. You just haven't put a name to it. So I'm going to let I be the integral operator, and I've given it sort of this strange way of expressing it, but it's going to be the traditional integral that you've always worked with, the Riemann integral from Calc 1. So what does it do? It takes a function and computes its antiderivative. Then my claim is that this is a linear transformation. Well, let's look at why. Okay. So if we were to, let's let f and g be integrable. Then if we were to take the integral operator and apply it to the sum of f and g, by definition, that is the integral of f of x plus g of x. And now I'm going to rely on the properties that we developed in Calc 1 that said I can distribute an integral over a sum. But then what is this expression right here? This would simply be what we got if we inputted f of x into the integral operator, and this one right here would be what we got if we inputted g of x into that single integral operator. Okay. So again, here's my f of x. That's just the integral of f of x dx. Yep. And here is my integral of g of x dx. That's what would happen if I applied the integral operator to g of x. But notice what we've shown. Okay. Notice that we've shown that if we were to start with, let me grab a different color here, maybe I of f plus g, we ended up with I of f of x plus I of g of x. So we've met this first definition of what it means to be a linear transformation. For the second thing we need to check, well, we could take I of some constant, let's just call it c, times f. So that's equal to the integral of that constant times f of x dx. And again, this is the part where you're going to feel a little bit of frustration because we've done this all along. Somewhere early on in a calc course, you learned that you can factor constants out of the integral, out of the Riemann integral. So I could rewrite this as c times the integral of f of x dx. Well, that's just c, and then here we have the integral of f of x dx. What can I replace that with? I can replace that with the integral operator applied to f of x dx. So if you're just looking at the first and the last step, you can see that we've met this definition of what it means to be a linear transformation. All right, I'll continue on in the next video with some more examples.